Okay, so we're getting ready for section 4.3, day 2. The no technology doesn't apply really so much. So here's the first example. It says sketch a possible graph for the function below without using a calculator. Find all the critical points necessary. So I want to emphasize that this is a possible graph. Now we know the function, so we can always plug values into the function to find how high our peaks are and how low our valleys are. But when I say a possible graph, that means we really don't care how high the peaks are and how low the valleys are. So let's take a look at that 5-step process, right? We're going to find, we're going to kind of work ourselves through that 5-step process and annotate our number lines. So let's take a look then at getting our number line set up here. Notice I have a second derivative number line here to help me with my curvature, my concavity, so to speak. So here's my function. There's its derivative, right? Bring down the 3x squared, bring down the 2 minus 6x plus 0. So let's grab our first derivative. Let's set it equal to 0 to get our critical points. So we set it equal to 0. Looks like we can factor out a 3 from each term and an x from each term. So I'm going to do, it looks like I divided out a 3. That's okay. So I divided a 3 here and I get 0. Now I have this expression. Now I can go ahead and factor out my x. So I'm left with x times x minus 2. I set both of those equal to 0. I'm going to get an x of 0 and another x of 2. So there are my critical points. When x is equal to 0, I have a critical point. When x is equal to 2, I have a critical point. That means I have possible mins or maxes at those locations, or a possible plateau, possible flat spot that isn't a min or a max. Going back up to this first derivative, there is no place in this derivative where it's undefined. We can plug in any value of x and it doesn't matter. A big indicator of undefined derivatives is to have a fraction with an x term in the bottom, so we don't have that. So we don't worry about saying anything about undefined derivatives in a formal fashion. So let's go ahead then and get our 0 derivatives on our first derivative line. And let's go ahead then and test, right? We're going through this first derivative test. We're plugging in a -1 here. So plugging that into the derivative, 3 times -1 squared minus 6 times -1, right? 3 times -1 squared, I'm referring back to this derivative, minus 6 times -1. This is 3, because this is a positive when it's squared. This is a positive 6, so we have a 9. That's a positive number, right? So we know we have a positive here. That's really all we care about, if you remember back from last week. Let's test here. So I'm going to test a 1. Okay, so my derivative value when x equals 1 is, looks like this is all going to be 3, and this is going to be minus 6, so -3. So that's negative. So I have negative here, so I go from positive to negative. So that definitely is a hill. Definitely have a hill going through this location. Let's try something out here, maybe 3, I think I do. Yep. So I stick 3 into the derivative expression. So I've got 3 times 3 squared. That's all 27. Minus 18. I know it's a 9, but I see a bigger positive and a smaller negative, so I know it's positive in general. So this is positive, so I go from a negative to a positive. If you watch me draw with my mouse, negative, right, sloping downward to sloping upward. So that's got to be a min in that location. So I'm going to go ahead and mark that. Again, my positive to my negative, positive upward increasing function to negative decreasing function. So that's got to be my hill or my max. And then negative to positive. It's got to be my valley. So there's my min. So I'm done with the first 3 steps in that process, and that's the first derivative test. So now I'm going to go through the same steps with the second derivative. So when I change the screen now, we're going to have our first derivative. We're going to take the derivative again. Okay, so we're still going to use our number line. This is where the second derivative number line comes in. So I wish I would have had the first derivative up here, but remember the first derivative was 3x squared minus 6x, right? So taking the derivative of that, then I get 6x minus 6. And I want to know where that's equal to 0. So I set it equal to 0. And this I'm solving in a more traditional manner. I'm adding 6 to both sides. I'll divide by 6. I get x equals 1. So at x equals 1, I have a second derivative that's 0. So I'm going to go ahead and plug that right there. So that's my inflection point. That means I must go from a smile to a frown or a frown to a smile. So is it smile to frown or is it frown to smile? Well, let's take a look at our second derivative values to tell us. So I'm going to go ahead and test a value over here. I can't quite remember which value I test. I hope it's 0. Yep, I test 0. So I put 0 into the second derivative. Remember, we're looking for values of the second derivative. That's going to tell us whether we have a smile or a frown. Okay, so 6 times 0 minus 6. That's what I'm doing here. 6 times 0 minus 6. So mathing that out, for lack of a better verb, that's negative 6. So I have a negative second derivative that's concave down. So this whole thing is a frown. That's concave down. Okay, coming over to the other side, just to be sure, let's test something over here. I think I test 2. I'm not sure. Yes, I do. So I'm going to plug 2 into my second derivative. So I'm going to go 6 times 2 minus 6. If you notice, 6 times 2 minus 6. Math all that out, I get 6. That's a positive number. So that's a concave up. So here we have a positive value for the second derivative. That's going to be our smile. So we know we have maxes and mins here. We know we have a point of concavity. Notice it's right between the max and the min, right? We're going to switch from a frown to a smile. So let's try to sketch this. I do have the y-axis here, but we really don't need it. I'm going to put a max and a min on my graph, okay? We could benefit from some more information. We do have the function here. We could find some y values, but they're not totally necessary because we just want a possible graph. They're not going to grade you on your locations of maxes and mins. So my max could be, if you notice the red dot going back and forth here, my max could be anywhere along that point, but it's a max, so let's put it up high. So I'm going to end up putting this point up high. And really, I put it here. If you notice, it's up 1, 2, 3, 4. If we plug 0 into here, don't we get 4? Okay, that's why I stopped the dot right there. And now let's put our min in. So I'm going to do the same thing. I'm going to fly a dot in here. Now my min's got to be smaller than my max. So notice my dot is not exceeding this location. Okay, it's got to be down here somewhere. Since it's a min, I'm going to put it low. So I'm going to just end up putting that dot down low. So I ended up putting it here at 2. Now I could plug 2 into here and get 8 minus 3 times 4, which is 12, plus 4. If you notice, I do get 0. That's why I stopped at the dot there, because I really do know the value. If you know them, great. If you don't, that's okay. Again, it's a possible graph. It doesn't have to be the exact graph. So here's my hill, here's my valley, my max and my min. I'm just going to go ahead then and get my point of inflection at this location, because a second derivative or a double derivative of 0 is a point of inflection. So I'm going to fly another point in here. I know that point of inflection has got to be between my max and my min. So I'm not letting this thing go higher than this, and I'm not letting it go lower than this. Okay, so I could go ahead and plug 1 in here and get a value. And I did that, and I got 2, so I let the dot rest right there. So now I know I need to go from a frown to a smile. So my function is going to look something like this. I'm going to draw it with my cursor. A frown looks like that, and a smile looks like this. And I'm not really going to care too much about anything else. So I've got a couple extra points here. I know I need something lower than the max over here so I can make my frown. And I need something higher than my min here so I can make my smile. Okay, we know that that's my inflection point. We're going to change from frown to smile there. So I have, here's my frown, and here's my smile. So that's the sketch for this function. Let's take a look at this one. This is a really common question. Notice what I'm giving you though. I'm giving you the derivative, meaning I'm not giving you the function. So this is a situation where you cannot find the max and the min because we don't know what the function is. All we know is its derivative. Now, last week we talked about finding the function, right? Big F, working backwards. But remember we introduced that plus c. So when we work backwards, we get a plus c in there. So we really can't even figure out what that c is. So this is one where we're trying to get comfortable with letting our maxes be up high and our mins be down low, and not really worrying about how high they go or how low they go. So we have the first derivative. Okay, we're going to follow our process again. We're going to go ahead with that first derivative test. Okay, and we're going to find the intervals on which f is increasing and decreasing. So let's get our first derivative test set up here. Here's our number lines to annotate our information on. Here's our x-axis. Notice I'm not giving you the whole grid anymore. I'm just giving you the x-axis so you can plot general locations. So here's the first derivative. There it is, 4x cubed minus 12x squared. We're going to set that equal to 0. And then we're going to solve this. So notice we can factor out a 4 and an x squared. And when we do that, we're left with x minus 3. So setting each one of these parts equal to 0, then we get x squared equals 0, which means x is 0. We get x minus 3 equals 0, which means x is 3. So at 0 and 3 is where we have the first derivative equal to 0. Those are our critical points. So that's this location and this location. So notice though we have an x squared equals 0. What that means is we have a repeated root at 0. That's a special location. So we actually have a 0 and another 0 at the same location and a 3 as roots. And so let's just see what that gets us. So here are our roots at 0 and 3. Excuse me, our roots are critical points. I said that wrong. And so now we need to determine what's happening there at our critical points. Is it a max? Is it a min? Or is it one of those flat points? Is it one of those plateaus? Because that's also a possibility. Just a glance at the second derivative, there's no fraction involved here, so we know it's defined everywhere. And so we don't have to worry about cusps or corners. We don't have any undefined derivatives. Okay, so let's take a look then at the points on either side. So let's plug in -1 to the derivative. I'm just going to remind you we don't have the function here. We can't plot function values, but we can look at the derivative. So I put -1 here. So I have 4 times -1 cubed minus 12 times -1 squared. Figuring all that out, that gets us a -16. So it's a negative value. So we have a decreasing function in this portion of our graph. Let's take a look at, what do? I pick 1 here. Okay, so 4 times 1 cubed minus 12 times 1 squared. 4 times 1 cubed minus 12 times 1 squared is -8. So this ought to be a kind of a red flag here. We still are negative. We still have a decreasing function. So this is negative going to 0 and then negative again. Let me draw that again with my cursor. Negative function going to 0, negative derivative, excuse me, going to 0, and then continuing negative again. So sloping downward, flat, sloping downward. So this location is a plateau. We'll see that in just a little while. I think I test a 4 out here. And when I test a 4 out here, notice my answer. I didn't forget anything. I just looked at this and said, wow, 4 cubed is 64, times 4 is 200 something. Okay, 4 squared is 16, times 12, that's littler. So this whole thing is going to be positive. I don't know what it's going to be, but I don't really care. So all I know is that it's positive, so we have an increasing function here. So at this critical point, when x is equal to 3, we go from negative to positive, right? Down, decreasing function to increasing function. So that's definitely a min. So in this case situation, since we don't have any switching occurring across this critical point at x equals 0, we have a plateau. And here we have a min. So we're going to go ahead and label this as flat. I only label it flat because plateau is too long to type. And I'm going to label this min. So that's our basic, our critical points, our basic starting points for sketching this function. Okay, so remember, we basically have gone through the first 3 steps of that process. So we're going to repeat those steps now. We're going to find the intervals where f is concave up or concave down. So we're going to take the derivative of this and look at the second derivative test. Okay, and we're going to use our second derivative number line to organize and annotate our information. So the second derivative, let's at the top of the screen here, I know it's down there, but bring the 3 down, right? 3 times 4 is 12, so we have 12x squared. And then bring the 2 down, 2 times 12 is 24, so we have 24x. Okay, so 12x squared minus 24x. So the second derivative test says set that equal to 0, and go ahead and solve it so that we can find our points of inflection. So I'm going to go ahead, and if you look at each term, we can factor out a 12, we can factor out a single x, and then we're left with an x minus 2. So solving this, that means x is equal to 0 or x is equal to 2. So we have 2 points of inflection at 0 and 2. So notice we have a point of inflection here where we had a critical point. That's why it's flat here. Okay, it's both a critical point, and it's also transitioning from smile to frown, which is why we have a plateau here. So anytime you see these zeros lining up on the first derivative and the second derivative test, and they're concurrent here, we have to have a plateau. Okay, and then the other point where we have a point of inflection is at 2. Okay, so looking at then testing this region and this region and this region, I think I test a -1 here. We're going to have to put that into the second derivative, right? We want to look at the second derivative, its value, and if it's positive, it's a smile, and if it's negative, it's a frown. So we're going to look at the second derivative. We're going to plug in -1. So we're going to have 12 times -1 squared minus 24 times -1. Let's take a look at this here. 12 times -1 squared minus 24 times -1. So mathing that whole thing out is going to give us a positive 36, right? This is going to be a positive 12. This is going to be a positive 24. We've got a positive 36. A positive second derivative means we have a smile. It's concave up. Okay. Now I come in here and I think I test 1. So let's put 1 into the second derivative, right? 12 times 1 squared minus 24 times 1. 12 times 1 squared minus 24 times 1. Mathing that whole thing out, this is 12, this is -24, we get -12. That's negative. So we're going to have concave down, since we have a negative second derivative. So concave down, we have a frown. And then I test out here, I'm almost positive I test 3. So when we plug 3 into the second derivative, 12 times 3 squared minus 24 times 3. I'm not sure, but I know this is bigger than this. I know this is 72, and 12 times 9 is bigger than that. So overall, I have a positive. I don't care what the value is, though. All I know is that since it's positive, it's concave up. So it's concave up. I know I have a smile here. So I've got everything annotated. I should be able to sketch this graph now. So looking at the sketch then, we know we need to have a, and we don't know where these y values are, and that's okay. So what we're going to do is we're going to sketch a possible graph. So we're going to put our plateau and our min somewhere, and then we're just going to make sure our points of inflection fall in a place where we can sketch a smooth curve. So we know that when the derivative is equal to 0, we need a min here. So I'm just going to put a little min down here. Okay, I know I need a smile in this region. I have a smile right there. Okay, that's a min. The only way you can have a smile is to have a min, right? We talked about that. So this is just going to kind of be my guide when I sketch. Okay. And let's see, the next thing I know that when my first derivative is 0 and my second derivative is 0, that I need a plateau there. Okay, so I'm going to draw, now this needs to be higher than this because this is my min, right? So I just drew it up here a little ways. And so I'm going to have remember I need a smile on this side. So if I need a smile on this side, that means I need to be coming down to this point. And then I need a frown on the other side, which means I need to start at this point and continue down. So you can start to see this basic sketch, and I'll draw it with my cursor, where I have this negative derivative, this decreasing function, and then it goes to a flat point, but then it continues to decrease, right? This is what this information is telling me. Decreasing function, I hit a flat point, and then it continues to decrease. So decreasing function, hit a flat point, continue to decrease till I hit my min, right? Continues to decrease until I hit my min. And then when I hit my min, I change direction because now I have an increasing function. So the second derivative, now, between this plateau and this min, I have to set up this point of inflection. So the second derivative is equal to 0. Somewhere between these two values is going to be my point of inflection. And so we just put it wherever we need it so that we can change this frown into a smile. Okay, so putting the pieces together then looks like we have something like this. Here's my half a smile, right? My half a smile while my function is decreasing. In this location, I have half a frown while my function continues to decrease. And then in this location, I have my smile until I meet my minimum, and then I start increasing my function. So that's a possible graph for what that function looks like.